There we go. Okay, so this is our second lecture. And just to let you know that I recorded the last lecture successfully and I posted that. So if you want to review the material there, you can. I'll also record today's lecture as well. I'll try to record every lecture. If you miss lecture, you can always, or even if you come to lecture and you want to review things that I present, then you can do that. So we pretty much covered Lab 1 last time, although we could talk more about the Linux commands, which maybe I'll do today. But so I'd like to go on to Lab 2, but if there's any questions that you have about Lab 1, why don't you ask them now if you want to? No? Okay. So let's look at Lab 2. Lab 2 is about expressions. You know, in computer languages, when you write code, the code is in the form of a sequence of statements. And these statements have substatements. And also a statement is comprised of components. And in particular, expressions. So an expression is something that's evaluated to something. I'll show you, like x plus y, that would be an expression. It's not a complete statement. If I say z equals x plus y, that's a complete statement, right? It performs some operation. X plus y, it's like a part of a statement. It would be like analyzing the grammar of a language. Like in English, you have a subject and a predicate. And you know, those are two components. And then you can dig into the predicate and say, well, there's a helping verb and a main verb and so on. So it's a lot like, you know, reading computer language is a lot like understanding the grammar of a language. So this idea that there are expressions, and expressions that we're going to look at are expressions that evaluate two numbers. And I have a link here to something called the operator precedence table. So when you formulate these expressions, you use these operators. So I'm going to look at mathematical expressions. All right, so here I am. I'm working at the terminal. And I'm going to CD into a folder that I created called 201. And this is some stuff that we did last time. It's still there. And we'll say we'll edit one of these. Instead of printing hello, let's print 1 plus, 2 plus 1 times 3. And then so that's C out. Now I'm going to print, so I'll talk a little bit about what I'm doing here. This is the basically the hello program that we looked at very briefly last time, and I didn't talk about what it is. I didn't talk about the details of it. So I'll talk a little bit about that now. So this is a complete C++ program. And this first line is called a pre-processing directive. And it says, search for a file called IOStream and just take its contents and paste it here at the start of this file. So it's kind of like a copy-paste operation. But it's recursive in the sense that if IOStream has include statements within it, it'll also follow those include directives and do a copy-paste operation there as well. And certainly IOStream as a file has many other include statements. And those include statements include other files that have include statements as well. So it's a big tree of references that connect a lot of files together. So this one statement here results in the inclusion of a lot of information that's taken out of files. So IOStream, once again, actually is a reference to a file. And this is a file that comes with your compiler. So as part of the definition of the C++ language. In the C++ language, you've got these primitive operations, rules about grammar, how the expressions are formed. But then there's also something called the standard library, which is functionality that's provided always to your program, such as how to open a file, how to close a file, how to print the standard output, and so on. So that's called the standard library. And all languages have some notion of a standard library to them. And we access the functionality from the standard library by using these include statements. We also use include statements to copy and paste from files that we make ourselves that are part of the programming activity that we're doing. So that's that first line. And the second line is declaring that the namespace std is being used. So we're going to use the namespace std, which stands for standard, so the standard library. So the standard library, all the names within the standard library that I just talked about are considered part of a namespace called std. Let me show you what I mean about that. I'll show you what I mean about that in a second. And then after that declaration here, we have a function declaration. The name of the function is main. And when this function, it represents a sequence of statements that are executed one after another, unless they're interrupted by some kind of a jump operation. And there are two statements in this program. This is the first statement, and this statement ends with a semicolon. That's a statement delimiter, delimit statements. Statements can be separated with semicolons. This is the second statement, and there's the ending delimiter for this second statement. So these statements they're like operations, they're like commands to the computer. Do this, then do this. And this is saying to do many things. It's saying to multiply 1 by 3, add the result to 2, and send that number through this output operator to what's called the standard output device. And, or standard output stream rather, not device. And that's it. That's what that statement, it's like a command to the computer. It says do this, and that's what it does. But as you notice, it's doing it in pieces. It doesn't do it all at once. There's parts to it. There's stages. So first there's this multiplication. And that right there, 1 times 3, that's an expression. Of course, that expression is part of a larger expression, which is 2 plus 1 times 3. That's also an expression. And so the result of this, you can look at that as that this expression evaluates to a value. And that value then becomes an entity or a thing that's used in the next expression that's evaluated. And that's this expression, which is whatever this evaluates to, well, which is 5. 5, the value of 5. That expression is, you can think of the computer as saying, like, as if the computer had a chalkboard and it erased 2 plus 1 times 3, and it replaces it with 5. So it's as if the computer was simplifying it, like you were simplifying a fraction or something. And then it carries on and says, well, what do I do with this 5? Well, I'm going to send it to this output operator that operates on this standard output stream, called cout. And this, by default, the standard output stream is your console window. So the 5 will appear on the console window. And then when that's done, we do the next output operation, which is to output a new line character. So ENDL is represents what's called a new line character. A new line character is something that you call a white space. White space is a character you don't see, but it has effects on the formatting. Whatever system is presenting text information to you, it uses these white space characters, such as spaces, end of line characters, tabs. These are all invisible characters. You know, like when you see an A, a B, and a C, those are visible characters. The program that's displaying those characters to you, they're looking at numbers in RAM. They're saying, oh, that's the number that represents an A. Oh, that's the character that represents a B. I'll just display those to the user. Oh, there's a character, there's a number that represents end of line. That's like a new line. That's what this is. When it finds that character, it says, well, okay, that means it's sort of the end of the line, and the next characters that appear in the data file should start from the left side and then be displayed going to the right. Those are called white space characters. Tab, end of line, end of file. There's a whole bunch of them. There's a lot of them. So these are two statements. These two statements here are, so look at how I indented them. That's because they're substatements of a larger statement, which is this function declaration, this function definition. I should probably call this a function definition. This is a function. The function is like a wrapper, a box around a collection of statements, a sequence of statements with jumps and loops and everything in there as well. So all functions are these sequences of statements that you may want to repeat over and over again, or maybe just call once, or never call. But when programs get large and complicated, it's helpful to group statements into blocks, separate blocks. And you do that using functions. So this is a function called main. And in main are these two statements. So we could have another function, called minor, and put other statements in there. And we can invoke the function minor, then invoke the function main, then invoke the function minor. And that way we have the ability to keep our code, our logic, our code organized, and also have the ability of re-executing a block of statements whenever we want. Well, now that's a topic in, I think it's chapter 3 of our book. Is that the chapter on functions, or is that chapter 4? Anybody know? Nobody has the book yet. Anyway, it's coming up soon. I think it's chapter 3. And so I don't want to get into too much about functions, because that's a topic that we'll be doing in a couple of weeks, all right? Or maybe next week. I just can't remember right now. So sort of tuck that idea away. So for now, for this lab, all of your code will be inside this main function. So it'll just be these lines. And notice these are indented, because these statements, these two statements, are contained within the main function. So we show that containment using indentation. Now, we could have done this. See this, I'm going to talk about this line here. 2 plus 1 times 3. We could have done this. We could have gone 2 plus 1 is 3, and then 3 times 3 is 9. I'll print a 9. Oh, it doesn't print a 9, does it? It prints a 5. Well, let's make sure, actually. I always like to make sure of things. So I'm going to use this C++ command. And you know what? I'm gonna rename this. I'm gonna move this hello program to I'll call it main.cpp. That's how you rename something from the command line. You can also rename a file from other ways. Now let's compile main.cpp. ls to display the contents of the working directory. There's a.out. So the compiler produced a file called a.out. Let's run that file. Let's run that executable. And it produces 6. Is that what I said? 6? Or did I say 5? So 3 plus 3. Because why does it turn out to be 6 and not 9? Yeah, multiplication has higher precedence. So here is these are called the C operators, which are also the C++ operators. By the way, the C language is a subset of the C++ language. And these operators have what's called precedence, which is if you see two operators together in the same expression, which operation do you perform first? Well, multiplication. In this expression here, we want to perform multiplication first because it has higher precedence. Here's addition. Its precedence level is 2 in this chart. And here is multiplication. Its precedence level is 3. So multiplication has higher precedence than addition. We do it first if we have a choice. Now, let's suppose we wanted to do the addition first. Then we could do this. We tell the compiler, oh no, we want to do the addition first. So we use parentheses to indicate that. So this is part of what you already know, because this is how we express operations in, say, mathematics, right? In the math that we've learned. So this should produce 9. Well, let's verify that. I'm always like to verify. So to verify it, if I run a.out, what's going to happen? This is a comprehension check here, and a debugging check. What's my problem with running a.out right now? Huh? I need to compile it. This is the old executable. I changed the source code, but I didn't recompile. I didn't regenerate the executable. So I'm running the old executable. So we're going to have to regenerate the executable from the revised source code. So we use this C++ command, a.out, 12. 12? Is that right? I got it wrong. Yeah. Oh, 4 times 3. Good thing I ran it. Otherwise, I would have thought it was 9. Okay, so this chart, there's a lot of operators in here, and like you'll see, well, this is function call, by the way. Look, this parentheses is function call. But there's another set of parentheses in here, maybe. It's not in here, so it's not considered an operator. This is called a typecast, and so on. Anyway, so there's that notion of precedence. Oh, but also, what about this operation here? Does that have higher precedence or lower precedence than addition? Let's see, because it does the calculation first and gets a 12, and then it sends it to standard output. So it must have lower precedence, this output operator. 5, so it has higher precedence. I don't get that. Why would that work like that? Oh, those are shift operations. Oh, this is C++, this is the C. So you won't be able to use it from that table. I got to think about that. But this output operation has lower precedence. That's why it's done after the addition and subtraction. I'm sorry, addition and multiplication. Now I want to come back and talk about, yeah, so maybe before I move on too fast, this table doesn't quite show what I'm trying to talk about right now, that output operator has a lower precedence than the mathematical operations. That's not shown here. And I need to think about that, maybe provide a different table. All right. Now, what about this namespace? Let's take it out. What does that mean? I just said, let's take it out, and then I put 2 slashes there. What does that mean? I made a comment. I turned this line into a comment. This is how we make comments. See that? Then you can have multi-line comments. So you can comment out this whole block. That's called a multi-line comment. Anything in between these 2 pairs of characters. This is where we open the comment. This is where we close the comment. That's a multi-line comment. So those are the 2 forms of comments in C++. It's the same mechanism for commenting JavaScript, and C only has the multi-line comment. Although I think newer versions of C provide support for single-line comments too. Other languages use exactly the same symbols for commenting. Java and C#, for instance, use these symbols for commenting. So by commenting out this line, we tell the compiler, oh, you don't need to think about this. Don't use this when you're processing the code and producing an output. This is just for humans to look at and understand. So what happens? We get a lot to look at here. And it's hard to see everything. So what I'm going to do is I'm going to redirect the output to T. It's just a file T. Oops. I have to use, this is called a standard output stream. I'm going to send it there. So this is the first error. Error, and it's giving me a line number. It says line number 7. Line number 7. And this is a column number here, 2. Error, use of undeclared identifier cout. Did you mean std cout? Because we took away that statement that said using namespace std. So we originally we told the compiler we're using the namespace std. So all the names that are in std, just let us access those names easily, freely. But we took that declaration out. So now the compiler wants us, needs for us to prepend the namespace identifier in front of all the names from the standard namespace. And cout is one of them. And this particular compiler is very helpful. You might get a different result in the labs or on your computers. You'll be, in general, running a different compiler than I'm presenting here. They have different ways of reporting problems and providing assistance. Here, the compiler is being very helpful because it actually has suggested the fix. So this cout is part of the standard library. It's in the standard namespace. So we prefix it like this. The same with this one. Same with endl. Oops. So now we get no error messages. By the way, what did I do to read my error messages? You know, before the the output was so long, I was looking at the tail end of the error messages. And it's hard to figure out what's going on if you don't see the messages from the very beginning. So I needed to access the very top of the error message output. So what I did was, instead of letting the output dump to the terminal, dump to the console, I said, oh, don't send it to the console. That's the default standard output stream. Send it to a file. And I did that using this operator right here. This is not a C++ operator. That's an operator that's supported by this console program that I'm using. And by the way, this is not the standard output stream. So this is saying direct the error output stream. There's another output stream called error, standard error. And direct the standard error output stream to the file T. Let me talk a little bit more about that. Now, we've just compiled this. This compiles okay. And let's run this. See, it says 12, okay? But it's being printed in the console. That's because this cout is the standard output stream. By default, the standard output stream is wired up to be the console. But we can change that wiring. We could say, no, let's change the standard output stream and set it to output to a file. Let's say output to a file called temp, or maybe temp.txt, because it's character data. So now when I run it, will I see a 12 or not? I shouldn't. So 12 is being written into the standard output stream, but I've redirected standard output to this file temp.txt. So you don't see the 12 anymore. But the 12 is in the file. That's because we once again redirected standard output from the console to a file. Now we go back to this. Let's put our bug back into the code. So this is the version of our code that does not compile. You see that? A lot of stuff got dumped on the screen. Now, C++, the C++ compiler that we're running using the C++ command, it's a program, just like our a.out. It's the same thing. A.out, C++, they're both executable files in the system. And the compiler is dumping the error message to the console. And so we should be able to redirect that dump of information from the console to a file, to temp. So we should be able to dump it to temp.txt. I'm sorry, that's a single symbol. But this does not work. See, it still dumped it to the terminal. And temp.txt, maybe that didn't, yeah, that got written over with nothing. The problem is the compiler is not dumping the error messages into the standard output stream. It's dumping the error messages into the standard error stream. And to redirect the standard, and by default, the standard error stream is associated with the console window. To redirect the standard error from the console to a file, temp.txt, we use this notation, 2 greater than. So this is like an operator. Okay, this is the left-hand side of the operation. which is this program. When this program runs, I'm not going to get into those details. So now the error output has gone into temp.txt. There it is. Now, and I did that so I could see the top of the error messages because it was scrolling. There was so many error messages, I was scrolling off the top of my console window. Let's fix the problem. I'll remove t. I'm going to remove temp.txt. So we're back to the beginning. Let's go ahead and compile this again. There it is. There's our program. Now, hey, if the compiler can do it, then we can do it. If the compiler can write to this standard error stream, well, we can write to the standard error stream. So what is the name of the standard error stream? I don't know. I'm going to guess what it is, though. I guess that it's C error. I feel pretty confident that that's it. Because I've seen it before. I'm just not sure of my memory. It compiles. I'm sure it's it. I'm sure we got it. So now, when we run the program, we still see the 12 because, once again, standard error by default is connected to the same thing that standard output is connected to, which is the console. So if we run this thing and direct the output to a file called T, we're directing now the standard error stream to the file T. Now if we look at T, there it is. There's the 12. It doesn't have the new line in it, though. Oh, yes, it does. Here it is. Sorry, it does have a new line. But let's suppose I send hi to cout. So first we send a 12 to the standard error, then we have a new line. We send hi to cout, and that's it. Let's see what happens there. So if we just run the program by itself, we see 12 and hi. If we direct standard output to T, we should just see what? Well, we won't see the high, so we'll see the 12. And if we direct the standard error to T, we'll see the high but not the 12. And if we direct, how do we direct both of them to T? I think you do it, I'm just going to guess. I have never done this before. It worked. I can't believe it. Okay. Always seems like magic. Oh, where's the 12? I don't know how to do this. How do you redirect both of those? I don't know how to do it. Anyway, it's not common that you need that. But I'm trying to explain about how these standard output streams are working. Now, there's another thing that we haven't talked about yet, which are the arguments to this main function. We actually don't need to use those in this course. When we write functions later on, then we will be using arguments. But for the main function, in this course, we won't be using these arguments. Of course, you're free to use them when you do experiments. What these arguments do is they give you access to the command line. So, you know, when you do things like ls tilde, you know, that's the contents of my home directory. That's different than doing ls where I am now, which is the contents of my current working directory, which is this 201 folder. So this command takes an argument. See that? That takes one argument. And you could have multiple arguments. I could say I want to see a long list, and I want to see hidden files. There's two arguments. And so now I see a different sort of formatted output from that listing command. These things are called arguments. Oh, the command runs, in this case here, with two arguments. So it'll take any number of arguments. Well, maybe there's some limit, 30 or I don't know, whatever. A program can access what's entered in the command line using these two arguments of the main function. So the information about what appears on the command line when the program is executed, you can access in code using the arguments to the main function. But once again, we won't need to use this feature in this class. But you may, if you're taking other classes that follow this one, then you'll need to use this. And almost all languages do it like this, similarly. Also, this name, main, what happens if we called it, you know, something else, like main or minor, I said, right? If we called it minor, what would happen? Well, it won't compile. It's not that it's not that the compiler can't understand the statements. It's that the compiler can't format the executable because the compiler won't know where to start execution. See, the main function is called the entry point. So you may have multiple functions in your program. And one of them is the entry point. That's where execution starts when your program runs. Has to be called main. That's the name of the entry point. It's like on Windows, when you're doing it, depending on the project type, you may have a different entry point. So other execution environments, you'll have different entry points. But for command line code, like what we're looking at, the entry point is a function called main. And most languages actually use that very name, main. So if you're working in Java, you've got a function called main. That's the entry point to your program. So if we don't declare main in our code, that means there's no the entry point is missing, and the compiler should complain about that. There it is. It says undefined symbols. It says main is undefined. And look at this. It's showing this name here, LD. That's the name of the linker. Actually, the compiler, the way we're using it now, is going through two steps. First, it generates what's called object code, and then it takes that object code and morphs it into an executable. And when it does that, it looks at references to functionality provided by the operating system. And it inserts this linker, inserts the right sort of commands and notations into the executable file so that when your code runs, it will properly access those functions that are available to the from the operating system, such as give me standard output. Give me the standard output stream. I'm going to write into it. So that sort of under the covers here, it's not something that we're doing directly. It's something that the compiler is doing for us. It needs to take our code. It needs to take this object code that was generated out of our source code and modify it so that that it connects with the operating system. And that's called linking. So this is a linkage error. Fix that problem. All right, let's go back. This is what you need to do. You have to do these exercises. And then when you're finished with these, send the source code to Jaron Willis and CC me. And that's how you complete this assignment. Let's start by looking at the first exercise. Let's look at how you're going to do this problem. Now let's start doing this problem together. I'm just cleaning up a little bit. I'm just going to keep my source code there. I don't need by.cpp. I don't need that junk. I'll just keep main hanging around. And also, I'm going to make a directory, mkdir. I'm going to call this lab2. And I'm going to cd into lab2. pwd, print working directory. It shows me, shows us where we are in the file system hierarchy. We're in a folder called lab2, within a folder called 201, so on. And at this point, I want to remind everybody that there is an exam, and on the exam, for the first time in this class, I'm asking questions about the Unix commands. What does ls do? Describe the Unix command mkdir. It makes a new directory. Okay? Got to know. You have to be able to write this as an answer on the exam. And there's some other practice problems there. So here it is. These are sample problems that have appeared. Actually, they're problems that have appeared on exams in the past. I'm just reusing them here. But the Linux commands are new. This is the first time I'm using those in my class. So I just showed you how to use this make directory command, how to use the cd commands, how to use the pwd commands, how to use the ls command. Well, there's nothing there, right? Let's use I don't want to have to write that main function from scratch. I want to start with a copy of a program I already have. So I'm going to use the cp command. I want to copy that main.cpp file into this folder and then use that for the first exercise. So I'm going to, that main.cpp is in the parent, see? I'll prove it to you. I'm going to ls ... Remember, ... means the parent folder. I want to see the contents of the parent folder. Of course, there's the current folder, which is lab2. That's part of the contents of my parent folder. But then there's the file main.cpp. I want to copy ... / main.cpp. I'm going to copy that to my current folder, make a copy of it. And the symbol for a current folder, so remember the format of this command is copy source destination. Copy from what, copy what to where. So we're going to copy that file to dot. What does dot mean? Current directory. Very good. Oh, let's verify that it worked. ls. There it is. We made a copy of it. I don't like the name because I got to email this to Jaron. I need to email him a file for this exercise, a file for that exercise, and so on to the end. So I'm going to rename this file. I'm going to use the move command and rename main to, maybe I'll call it lab2 exercise1.cpp. Just to make sure he knows it's lab2. If you want, you could just use ex1. Maybe that's easier. So moving and copying, that's, it's a little different. So Moving is like cut and paste. Copy is like copy and paste. So here we have this ex1.cpp, and let's get ready to solve the problem. And I'm just going to get my execution environment set up here. I'm not going to actually even read the problem yet. I know it's asking me for one file of source code. Let me just make sure. I'm going to CD in the lab. I've got two like virtual screens open. See, I've got that one and then this one. I can bounce around. I'm using the Screen program in case you want to learn how to use that. It's called Screen. And so let's see that this thing builds. It builds. Let's see if it runs. It runs. Now there's another way to write this. We can cascade this output operator like that, just to show you that it can be done. So the first thing we do is we output OK, and then we output the new line character, or end line character. It's called a new line. Let's see if that has the same effect. It does. So we can do this because this expression, oh, by the way, we have the same operator. That output operator there, this output operator there, they're the same operator, so they have the same precedence. They can't have different precedence, right? So you got to use a different rule to decide which one runs first. And the rule is go left to right. So if two operators have the same precedence, if they're left to right operators, then evaluate them in left to right order. And most operators are left to right. There's some that are right to left, but most are left to right. So actually what happens is this first output operation is performed first. The second is performed next. But the output operator needs two things. It needs an A and a B. It needs a left-hand side output operator and a right-hand side. That's the general structure of that statement, of that expression, using output operator. So how is it that we can add on something else? How does that work? That's because this expression here evaluates to, when it runs, it actually, expressions evaluate to something. They're replaced by something. Right, I was talking about it earlier. 1 plus 2. It's as if the computer wrote it on the chalkboard, 1 plus 2, and erased it, and it wrote the number 3. That's what I mean by evaluates to. The expression, in a sense, is replaced by a value that it computes to. So this expression computes to something. It computes to the left-hand side. That's it. So the computer will evaluate this, which has what we call a side effect. It sends the right-hand side to the output stream LHS. And then after that's done, the expression is replaced by this. That's why after this first out is printed, this whole expression is replaced by cout. Now, cout is the correct left-hand side of the next output operator. So that's how you get that cascading effect. And there's other operators, other languages. Most other languages use the same mechanism. A lot of what you're learning in here is techniques that you can carry over to practically every other language environment that you're going to work in. That is, if you do any programming. All right. So we've got our sort of our environment set up. We figured out how to do compilation. Now let's start solving the problem here. We have like a skeleton program. We have the shell of a program. Now we can start working the details out, the additional logic that we need to solve this problem. Just wanted to get the setup of our execution environment, out of the way so we don't have to think about that. Make sure that main is typed in correctly. Using namespace standard is done. So you just write this little hello program, make sure that runs. Okay, now let's do this. Write a console program. So it's a program that runs in a console, not a program that creates an application window. Programs that create application windows are called graphical programs. We're not creating graphical programs. We're creating console programs. They run in the console window. Write a console program that prompts the user for 3 double precision floating point values, x, y, and z. So when we run the program, it should ask the user for what is x? And then the user types it in. Then it says, okay, what is y? The user types it in. What is z? The user types it in. And then the program computes these values and displays them. To access the built-in functions sine, cosine, and log base 2, you need to include the CMath header at the top of your code, which is this. So we know we're going to need this. So let's go ahead and put it in there now. And that's the end of the problem statement. There it is. I just put it up there with the rest of the include statements. And notice I put a blank line there. It just makes it easier to read. And here, this using statement, I have another blank line, and I start the function. Well, this is a blank line because I'm preparing to type something in here. Let's prompt the user for the value for x. It says x equals. Well, it doesn't read anything in it. It just terminates. It just does x equals. So it's prompting. So to prompt the user for something, we just use what we know already. Instead of displaying hi or hello or bye, we're going to print x equals. But now we need to pause and get input in from the user. And we do that using a standard input stream. A standard output stream, by default, is connected to the console. The standard input stream, by default, is connected to the keyboard. So you can redirect that, by the way. The standard input stream could be another file or a socket or something else. So the standard input stream, and this is the input operator. So pull out of the standard input. You can think of the stream as a sequence of data, bytes that are just sort of streaming into the program. And it's going to back up and wait for the program to start to read those bytes, to read that data. It's as if there was a dam there, and we're damming up the stream, and we're in charge. We pull out of the stream what we want, but what we pull comes in sequential order. So we want to read that into a variable called x, but wait a minute, we need to have x needs to exist. So we need to declare x. And we do that like that, int x. We're saying to the compiler, I need a storage location to store an integer number, a 4-byte integer number. And I want that storage location. I want to be able to, and please, I want to refer to that storage location with the name x. That storage location in memory that I'm going to refer to with the name x. Compiler, make that happen. And then I want to use that storage location x, that variable x here. Here I'm telling the compiler, grab an integer from the standard input stream, copy its value into variable x. Compile and run. See, it didn't terminate. The prompt is not being displayed. It's waiting for me to enter a number. And that the program hasn't gotten a number yet, but as soon as I hit return, that input operator will complete. So we read in the value 1, 2, 3. We want to get the values x, y, and z, and then display the sum of x, y, and z. So let's do like this. So after we read in x, we're going to compute x plus y plus z. And then after we do that, then we're going to print the result. So to compute, well, we need x, we need y, and z. So let's go ahead and do that real quick. So we need y and z. And then compute x plus y plus z. We can do it like this. Let's declare another variable. Wait a minute, are these integers or real numbers? Oh, 3 double precision floating point values. So not integers. We need to allow decimal numbers. So let's fix that in a moment. Let's do it with integers first, and I'll show you how to do it with floating point numbers. Floating point number is a number that has a fractional component, like 1.5. An integer number is a number that's a whole number. Or an integer is an integer. It could be -3 or 0 or 9 or 99, but it cannot have a fractional component. So the result is x plus y plus z. Let's print the result. So it's cout. Let's have a little information to the user. We'll say x plus y plus z equals, and then we'll print the result. And then let's have a new line there as well. Oh, there it is. We could replace x, y, and z with 2, 2, and 3 if we wanted to in the code. I think this is good enough. All right, that gets that one. You see how that works? And then we just go through here and do the rest of these. What's the sign of x? Oh, I want to talk about floating point numbers. Sorry. (1.5). Look at that. The function, the program is malfunctioning. Now in this class, we're not going to worry about checking for valid input, just because we have too many things to learn. But if this was a real program that you were going to use for some work that you were doing, you would want to check, you would want to see that the user has entered in an invalid number. So when we say read in an integer, and actually that input operation is failing. So we're getting some malfunction here. So we have to check for that failure before we go on and assume that x, y, and z are valid. Before we go on and do this, we have to check that these input operations succeeded. But actually they didn't. In this case, they didn't succeed. I'll give another example. I could put in R. I've typed in, that's not even a number. So the program is malfunctioning. But once again, we're not going to look at checking for validity in the input. But that's something that's worth learning about. And I actually used to cover that in this class, many years ago, but I sort of cut it out because I want to focus on other issues. But we can solve the problem here, not the problem of verifying correct user input, but the problem that we haven't solved the problem statement correctly because we're using integer variables. We need to use double precision floating point variables. And we use the keyword double for that. X is a variable that holds a double precision floating point number. Same for Y, same for Z. Same for result. These are floating point numbers now. Now let's try it. 1.5. Oh, look, now it's behaving well, right? So 2.5 minus 2. That looks right, 2. All right, what about the sine of x? So let's have another result, which is the sine of x. And we can do this because we included this CMath header. Inside the CMath header is a declaration of the sine function. So, and by the way, I'm deliberately introducing a compilation error here. So see if you can spot it. I have deliberately introduced a compilation error. Do you see it? Anybody see it?
Result is declared twice.
Huh?
Result is declared twice. The variable result is declared twice.
Oh yeah, very good. Thank you. That's good. I got bad ears, by the way. It's not you, it's me. Okay. That is correct. The variable result is declared twice. We want to continue to use result, but we don't want to declare it. So we just use it. We don't declare it. This is where we declare it. This is where it's born. We tell the compiler, let this number be, result, this variable called result. And we can't say, let another variable be called by the same name. I said, no, we can't do it. We cannot give the two different variables the same name. They have to be, the compiler needs to distinguish between the two variables. So we can't give two different instances of a double the same name, unless we put them in different namespaces. The STD namespace is just one namespace. It could actually declare another variable inside a different namespace. But we're not going to get into that. That's an advanced topic. So let's see if this works. And let's see, this is, there we go. All right, sine of, let's put in a known value. Sine of 0 is what, 0? Is that right? Sine of 0, 0. And sine of, is that right? Sine of 0 is 0? I don't even remember. So, and y is 1 and z is 2. Yeah, sine of 0 is 0. And let's try sine of pi. That's 0, 2. How about pi halves? Let's do that one. What's pi halves? It's approximately 3.14 divided by 2. So it's 1.5 plus 7 is 1.57, like that. Did I get that right? Yeah, look, sine of that is 1. That's pretty good. And if I got off a little bit, what happens if I went 3.56? Oh, it's a little off there. All right, good. So you say I'm testing, right? I'm doing tests here to verify that I understand it. And notice that the variable that is the value that's passed into the side function is in radians. And we just verified that. It's not degrees, it's in radians. So carry on with this. You've got other expressions to code and evaluate. And then you move on and do exercise 2, exercise 3, and so on. And I'll talk more next time about the other exercises. I'll talk about this RAND function that you need for that. And also look at exercise 2, just briefly before we break. I made this look exactly like exam 1, although I did not include problems related to Linux, okay? This is just an old exam that I had in the past, and I turned it into exercise 2 in lab 2. So you can practice preparing. This forces you, requires you to practice preparing for the first exam. So you need to do these problems and then create a text file. I mean, like exercise 2.say txt, something like that. And then put your answers in there for Jaron and I. It'll like say something like this, you know, whatever. So your answers will look like that, and then just send that file with the other files for the lab. You don't need to include all this stuff, just the answers. Any questions? Question?
When we send it to you, whatever way you want it in the subject line.
Yeah, put in the subject line for lab 2. Yeah, CC me. Don't mail it to me. Mail it to Jaron. CC me. Oh yeah, have your name in there. In the body of the, you can put your name in the subject line or in the body of the email. You need to have your name.